Hello and welcome to the task Shader Chopper. In this task, we will build upon our previous task of building a chopper, but now we will add a gradient to our cuboids. As you can see here, this body of the chopper on one edge is lighter than on the other edge. We are not doing light calculations yet. That will be in the following chapters. But we will be writing shader code to control the specific colors of the vertices and the fragments. In vertex shader, what we do is we transform the position from local space to clip space. We will talk about what the local space and clip space are in future lectures. To do that, we apply the model view matrix and then projection matrix to our local position. We will see how it can be done later when we are implementing the shader. In the fragment shader, we take the data that we calculate from the vertex shader and assign the colors to the pixels. I'll give you a brief explanation of the spaces that we have to deal with in the vertex shader. So let's say we have an object in our world, and this object will have a local space, the local coordinate space. All the vertices in this object are defined in this local space. So for example, this vertex might be 1, 1, 1. But this object has a rotation and a position in the world, which origin might be somewhere else. So the transformation from local space to world space is called the model matrix. But then in this world, we also have a camera. And we want to transform the locations from the world position to the camera position. So the subsequent transformations are easier. And for that, we use the view matrix. And finally, the vertices in the camera space have to be projected onto the screen. And for that, we use a projection matrix. So let's say that this 1, 1, 1 is our vertex. And we need to multiply the matrices with the vertex. So first we apply the model matrix. Then we apply the view matrix. And finally, we apply the projection matrix. The parenthesis here indicates the order of operations. We apply the matrices from right to left. But usually we don't include the parentheses. So let's write it without it. And in shaders, we want to do as little as possible. So we might pre-multiply some of the matrices. For example, if we pre-multiply the view matrix and model matrix, then we get model view matrix. And if we multiply also the projection matrix to the model view matrix, we get the model view projection matrix. And that multiplication is our main output of the vertex shader. Now let's look at our base code. This is very similar to the code from previous tasks, except now we also have files for our fragments and vertex shaders. Those shaders are included on those lines on 29 and 30. And they are put into global variables, which we'll be using later. The throw, you should copy the same thing that you had in previous task. The create hanger and create chopper should also be the same. So copy from the previous tasks. And finally, the create cube. This will be different in this task. We'll talk about that later. But in the end of the create cube function, there is this shader material that we'll be using, and that is a material that will use our defined shaders to determine the positions of the vertices and the colors of fragments. As you can see, we are using our global variables here, vertex shader and fragment shader. So let's look at the vertex shader first. The vertex shader has one function, the main function, which will be called for each vertex that the material is assigned to. And we also see that there are two global variables here. We have an attribute vector3, the vertex color, and then varying vector3, which is for interpolated color. There is also a third sort of global variable called uniform, which I will explain now. Let's say that we have three vertices which form a triangle. So for each vertex, we run the vertex shader. And for each fragment, let's say those are the fragments in the triangle, and we run the fragment shader. The attribute variables are unique for each vertex. So let's say that we have three vertices. We might say that this first vertex has color red, the second vertex has color green, and the third vertex might have a color blue. So attributes can be used to determine what the color of each vertex is. But in future, we will also be using the attributes for other things other than color. So it's not exclusive to colors. The varying variables are unique for each fragment that we use the fragment shader for. And those varying variables are the output from the vertex shader. So we assign a value to a varying variable in the vertex shader, and then this is interpolated between the vertices to get the interpolated value for each fragment. So let's say we have a fragment here. So this will be interpolated from those three vertices. As you can see, this fragment is closest to the second vertex, so it means that its its value is closest to the second vertice's assignment to the varying variable. And finally, we have uniforms. Uniforms are constant values for all vertices and fragments. So if I set a uniform value in my JavaScript code, let's say it will be an integer, and I assign it value to 5, then all the vertices and all the fragments will see this uniform value as 5. As we saw from the description of the task, we have to determine the location of the vertex, which is also the number 2 task in this file. So what we need to do is we need to take a vertex position, multiply it by model view matrix, and then by the projection matrix. As we saw, that those should be uniform values, so uniform matrices, but they are not here. We can find them in the WebGL program boilerplate. So QGIS appends those values to all the vertex shaders or fragment shaders. So for vertex shaders, all those uniforms are added. We see that the model matrix is added, model view matrix, which is the multiplication of model matrix and view matrix. We have projection matrix, view matrix, normal matrix, which is for transformations on normals. We also have a camera position. And then we also have 3 attributes. We have a position that we'll be using as the local space position of the vertex. We have a normal, which we have not defined in our task. And then we have UV, which we'll be using in future tasks for texturing. So the task says that we need to take the vertex position, multiply with model view matrix, and then multiply with projection matrix. And at the end, we also have to apply this value to GL position. So first we take the position attribute, which we remember is unique for all vertices. Then we need to multiply the model view metrics to it, and model view metrics is in this variable. And then we need to multiply the projection matrix to it, and that's over here. But as we saw, the position has type vector 3, but the matrices have type matrix 4, which means that those cannot be multiplied together. We can do that by using the vector 4 constructor and assigning the fourth coordinate to 1. Now we can see if it works. First, we need to assign here a color. So we see GL flag color is the variable that we need to assign to. Let's initially assign it to completely red. As we see, the chopper is red, but we see it, which is good, because that means that our transformations produce the correct positions onto our screens. To illustrate the varying variable, we could assign it the position of our vertex. Since our vertices are always between -1 and 1, or our coordinates are between -1 and 1, means that we can normalize them to 0 and 1, which means that the colors we see should be black to white. So let's say that the interpolated color is our position, but now we have to normalize it with 3 and the vector of 1. Finally, we multiply it by half. And in our fragment shader, we use this instead of red. Now, if you look at the output, we see that there is gradient. So since white color is here, I can safely say that this is in position 111. But this is only blue, so that means it's 001. And this is magenta, which is mixture of red and blue. So this is 101. So the task you have to do is firstly create two different colors. We have a dark color, so you need to also create a light color object. Then the first thing you need to do is create the array that you hold the colors in. This can be done with float32 array, but you also need to calculate the correct size beforehand. So that depends on the vertex count and also how big the color variable for each vertex is. Then you need to assign colors to all the positions in this array. And you have to make it so that the gradient for the blades is darker in the middle and lighter at the ends of the blades. So you might also need to change the rotation of the blades in the grade chopper function to achieve that. And finally, you need to call geometric set attribute with correct variable name, and also assign the created float32 array to it. So the variable name should be our attribute, the vertex color. And then the task should be completed. And that's it.